So let's go ahead and dive into our low current and high resistant measurement techniques. So what I want to cover here is some sources of measurement error. So this is a little bit of measurement theory here. But what we get errors like electrostatic interference, leakage currents, self-generated currents, that would be internal or external offset currents in the system, triboelectric effects, piezoelectric effects, contamination or humidity on our cables or test fixtures. And then we talk about source impedance, that'd be source resistance, source capacitance. We had a conversation at lunchtime about measuring the electrical impulses from human nerves. It was a great conversation, and from a measurement perspective, it's very interesting because one of the things that I don't personally know is I don't know what is the source impedance and capacitance of a human nerve ending. It obviously is generating some voltage impulse, which is traveling through the system, and there can't be a lot of current involved there. It's just not, so it's got to be a relatively high impedance source. It can't drive a lot of current. So it was an interesting conversation about how do you actually go and measure some of these impulses on human nerves. Now, I have to immediately make another disclaimer. So, our instrument is a characterization tool for semiconductor devices and materials and inanimate objects. In no way do we ever recommend you hook that up to a human, okay? Yeah, we do it in Keithley labs just for the fun of it once in a while, but the truth is Keithley strongly recommends this was not designed to be tested on animals or humans, okay? No matter how much fun it is to hook it up to your undergrad lab partner and see his hair curl, okay? We never recommend you hook this up to anything but inanimate objects. So what is electrostatic interference? Really, electrostatic interference is that voltage that is generated through some source related to the capacitance on our measurement system. So if we had a capacitance on our system and some electrostatic voltage source, the actual current in our reference signal conductor is the capacitance times dV/dt plus the voltage times the change in capacitance dC/dt. In other words, we got to get stuff to move here in order for the current to flow. All right? So typically electrostatic interference occurs in really low current measurements or really high resistance devices. Because electrostatic interference really it's a really high source impedance. It doesn't have a lot of energy behind it. Unless it's a lightning bolt or something, but we don't have many of those in the lab, hopefully. The best way to reduce electrostatic interference is to build a shield to enclose the box under test. So, many years ago, Dr. Faraday came up with this concept of the Faraday cage. And basically he said, if I take and I completely surround a node and I ground that, then that electrostatic fields have no ability to generate a field inside that enclosed cage. That's the Faraday cage. And so by surrounding things with shields, no electrostatic fields can generate fields inside that shield. So that's what this shield to enclose the circuit does for you. Just a simple metal box or even a meshed screen. And the shield itself should be connected to circuit low. You recall from this morning's conversation that we defined circuit low as the common point on the system. And that common point may or may not be earth ground. Okay, but it is a well-defined common point on the back of the instrument. And if the jumper's in place, then it is earth ground. If the jumper's not in place, it's that point on the back of the instrument, which you need to run a wire from that over to your probe station or your electrostatic shield. Now, electrostatic interference is a lot of fun. I call it the boss effect. Okay, I guess in a research it would be the professor effect, maybe. So you've been sitting working on your sample and taking data, and all of a sudden your data looks good. everything. Oh, my sweep is good, my data is good, my curve's good. You know, boss, professor, come over, take a look at this. The professor walks over and the data goes bad. Okay? That's his electrostatic field. He's unshielded. He comes over, he changes the entire electrostatic fields around the entire system. Okay? Of course, the professor or the boss says, what are you talking about? You don't know what you're doing. So, but you can avoid that by simply having very good shielding. Now, modern probe stations have taken this into account. The expensive modern probe stations take it into account. They build little local electrostatic shields. Now, in the old days, we used to take the entire probe station and we would put it inside a big box called a light-tight enclosure. And we'd hook everything up, we'd set the probes down, we'd close the lid, and then we'd come over to the instrument and we'd make the measurement. And that whole light-tight enclosure was our electrostatic shield. I can't tell you how many times I've seen electrostatic shields, light-tight enclosures, not connected to the instrument. It was just sitting there floating in space. It could go anywhere it wanted to go. So you have to make sure your electrostatic shield is connected to the common of the instrument. A little bit more on shielding. So connect the shield to the common of the instrument. If the circuit low is floating above ground, you need to add a grounded safety shield around the electrostatic shield. Remember, this instrument does not have to be ground referenced. In some cases, you don't want to ground reference it. It kind of depends on a lot of factors that I won't cover here. But if you disconnect this common of this instrument from earth ground with the jumper link on the back, and then you take that and you connect it to an electrostatic shield, there's nothing holding this whole system with reference to earth ground. The whole shield could float up anywhere that it wants to float up to. And what most commonly happens is you get a static shock from it. You wind up, you touch it, and you get a static shock from it. It's floated off of earth ground. Well, that static shock might be uncomfortable for you, but I can tell you it's devastating for anything that's inside that box, any samples and devices. So we want to use shielded cabling between the high terminal and the device under test. Does that mean we don't need shield cabling on the low terminal? In general, no. The low terminal, by definition, is what we call a low impedance to ground. It has a finite amount of capacitance and resistance to earth ground, and it's not making any measurements. So it really doesn't pick up any electrostatic fields. But the high terminal is where we make all of our measurements, and that's the one that needs to be shielded. So you want to use good coax, triax shielded cables. You mentioned you're from India. I was in India a couple of years ago, and I was surprised at the variety of probe stations that you find in the different research institutes there. Things that have been around for a number of years, things that have been cobbled together from whatever pieces happen to be available. We saw one case where there was a piece of wire stuck in the back in the triax connector, run over to the probe station. A plain piece of wire, okay? There's not a chance that that thing could ever make a good measurement, you know? So, but, you know, if somebody doesn't understand the basics of measurements like we're teaching today, and if that's all they have, they're going to try and hook it up and try and get the measurement, and then perhaps not understand why it doesn't work. Okay, so to minimize error currents due to electrostatic coupling, you want to keep charged objects, including people, away from the sensitive areas of the circuit. You want to avoid movement and vibration, and you want to shield your device under test and connect that to the circuit common. This is not electrostatics, but it's a fun story anyway. So we had an advanced research scientist in Holland, and he was doing some very precise measurements. He did measurements doing matching measurements. And one day he was standing next to his pretty well shielded probe station, and his cell phone rang. And he saw his measurements jump and change. Now his measurements only jumped by in neighborhood under 0.5%. I mean, most people wouldn't even see it. But it turned out that even though he had a shielded probe station, there was enough energy generated from his cell phone that when the cell phone rang, hence the RF engine turned on and started transmitting, that was able to actually generate enough signal to go in and impact his measurements. By the way, one of the results from that, he published a paper on it, one of the results from that was the probe station company went and improved the shielding on their probe station. So, this is just an example of what we call an unshielded measurement. This might have been that piece of wire that we talked about. Somebody stuck a piece of wire in, ran it, there's no shielding. If they walked by it, if you walked by it, you would see this noise bounce up. This is probably somebody walking by here, okay? It could be somebody turning the light on. It could be anything. If you're unshielded, almost anything can cause significant noise. Notice this is in the range of 4 nanoamps. Now, to us in the semiconductor business, 4 nanoamps is huge. I mean, that's, this is more signal than drives my whole device, right? To the rest of the world, 4 nanoamps doesn't even exist, right? But to us, it's huge. This is the same thing when we have changed no other settings except we shielded the system. Now, we very commonly will see people get an unshielded system with noise, and the first thing they do is they say, oh, I got to go to quiet mode. So they click on quiet mode. And guess what? Quiet mode will integrate a lot of this noise out. Okay, that's one way to do it, but you're much better off taking care of the noise at the source than trying to use the settings of the instrument to bring it down. Okay, the second great thief that we have in our industry is what we call leakage currents. These are air currents that flow or leak through insulation resistances when voltage is applied. This is generally an issue when the impedance of the device under test is comparable to the impedance of the insulators in the test circuit. So the conversation that we had in lunch when we were talking about measuring the voltages on nerve endings, okay? Well, that's a particularly difficult thing to do because the nerve ending is a relatively high impedance device. That means the sampling head, whatever the sampling head is, has to also be a very high impedance device, or what it will do is it will simply discharge the nerve ending and none of the signal will get out where we can measure it. So the impedance of our device and the impedance of our cables and the impedance of our instrument, it's important to be aware of all that, particularly when impedances get high. So to reduce leakage current, we have to use good quality insulators in our test circuits, reduce the humidity, and use guarding. So I was picking on you a little bit in India, but I'm going to pick on Malaysia now. So back in, it was like 1993, I went to Malaysia, one of the universities there, and they actually had the Keithley quasi-static CV meter, and they were trying to make measurements on MOSFETs. And the data was just moving all over the place. And so, we happened to be paying a courtesy visit there, and we went in and we walked into the lab, and it's got to be at least 90 degrees Fahrenheit and probably 90% humidity, and all the windows are open in the lab because they didn't have an air conditioner in the lab. Okay, so the humidity is all over the place. Every connector, everything is contaminated with humidity, and who knows what else. All right, there was absolutely no way to make that instrument work. Every circuit board in the instrument was actually coated with moisture. Okay, it's a high impedance, low current instrument. Absolutely couldn't work. But they needed to get the measurements. So what we did is they had a very small closet back in the corner. So we went, we emptied out the closet, we put all the instruments in there, we cut a hole in the closet, we put a window air conditioner in that hole, we pumped all the heat and humidity out of the closet, dumped it out in the lab, right? And then we had this nice little closet that had a humidity control room, and we were able to make the measurements. So humidity is a huge, huge problem for high impedance or low current measurements. Okay. Now, most modern labs, particularly, certainly here at Purdue, they have air conditioning, controlled environment, but the truth is the facilities probably doesn't always have great control in the lab. A lot of times I'll see a facility will shut the air conditioning off at night and the lab will go to 80 degrees Fahrenheit and 60, 70% humidity. right? And that humidity sort of coats everything. It coats the circuit boards, it coats everything. And then, of course, the next morning at 8 o'clock, 7 o'clock in the morning, they turn the air back on. The whole room comes down. You come in at 9 o'clock, or if you're like some students, you come in at 10 o'clock. And you know, it seems like it should be good, right? But everything has been soaking in humidity all night. So one of the things you definitely want to manage in your laboratory is maintaining the humidity and temperature around the clock. Okay. I had another example. We were at actually a semiconductor facility, a fabrication facility, and they were actually an advanced memory facility measuring leakage on their devices. And they wanted to get leakage in the sub 100 femtoamp regime. So it's pretty small leakage currents. Okay. And so we're in there, and this is when this instrument was relatively new, and we had our little preamplifier, and we were comparing that to an older generation instrument, and we're measuring, and it's a pretty nice day out, and it's kind of, humidity's running about 30% outside, and that evening a thunderstorm came through. And the humidity changed rapidly from about 30% outside to maybe 70% or even 80%. Okay. And the air conditioning couldn't keep up. And so the room changed. And so we came in the next day, and the older generation instrument wouldn't measure anymore. I mean, it was up at picoamps. And we're going, what happened? Why is the Keithley still working and this older generation not working? Well, it was because that humidity changed overnight. It contaminated enough of that instrument that it hadn't recovered yet. Okay. But Keithley's preamplifiers are hermetically sealed. So we didn't suffer from that particular contamination. So you'll see that a lot, and it shows up a lot, particularly in quasi-static CV measurements. All right, so a number of years ago, there was a concept developed. You know, I'm not sure who actually developed the concept of guarding, but Mr. Keithley was certainly one of the first people to actually use the concept of guarding. One of the first instruments Mr. Keithley developed was in 1946, was a product called the Phantom Repeater. And it was a high input impedance amplifier. And it was a phantom repeater because it was invisible to the signal, right? And it used the concept of guarding. So there's really, I don't have any historical data that says who invented guarding, but certainly Keithley was one of the first to use it. And guarding works like this. A guard is a conductor that is driven by a low impedance source whose output voltage is at or similar, very close, to the voltage of the signal of interest. So the guard terminal, which is the inside shield of a triax, is used to guard not only the cable, but also the test fixture. So guarding works like this. Let me see what I have next here. Here's a great example of a guard. So guarding works like this. Imagine I've got a source measure unit with a voltage source and a current meter. And coming out of my output high into a coax cable, I've got my signal coming out here through my DUT being returned back to my common. Okay? Now my coax cable has some leakage current. It's a coax cable, right? Surrounded by a nice electrostatic shield. For the electrostatic shield to be a shield, remember it has to be tied to the common. Okay? So what I have is I have a parallel leakage path right by my DUT. But my measurement is taking place back here. I'm measuring all the current coming out of this thing. So I'm measuring the current through the coax cable and the current through the DUT. Now, we all work in the materials semiconductor business. We have materials and devices that frequently this can reach 10 to the 9th or 10 to the 10th or 10 to the 11th ohms, right? Most cables aren't that good. Most coax cables aren't that good. Even Teflon cables, they have leakage paths in the connectors, etc. So a guard works like this. I'm going to take that and turn it into a triax cable. I'm going to put a 1X, a unity gain buffer amplifier here, so that the voltage that I'm putting out here is the same voltage here. And I'm going to apply that voltage to the guard, which used to be this shield, but now it's a guard. So now I've got the same voltage out of the high as I have out of the guard. In other words, I've got 0 volts across that insulator. I can have no leakage current. By the way, I can have no capacitance. I've got 0 volts across there. The capacitance is guarded out. The leakage resistance or the leakage current is guarded out. But the problem now is the outer shield of my coax is now hot. It's now at the same voltage as my conductor, right? And that creates a safety problem. So what I have to do is I got to wrap another shield around that and tie that to the common. Hence we get the triax cable. This outer shield provides us both with electrostatic shielding, but also a safety shield from the driven guard. And that's what triax cable does. So now all the current that flows out of output high cannot flow through here. It flows through the DUT. But you say to yourself, well, wait a minute, this insulation in this outer conductor is just as bad as this insulation was here. Don't I have all that current flowing here? The answer is yes, you do. But that current's being supplied by a unity gain buffer amplifier, which can supply as much current as this thing needs. And that unity gain buffer amplifier is extremely high input impedance. In other words, there's no current flowing into that buffer amplifier. That's called a guard amplifier. This is a driven guard, a DC driven guard. Okay? It guards out leakage current and it guards out capacitance. Now this concept of a guard can be extended out to your test fixtures. In fact, frequently in a research environment, I'll see people build custom probe stations and custom test fixtures where they actually go and they put guard rings on things and they go and they want to get their electric fields exactly where they want them. And you'll see that in CV structures. Well, they'll put a guard ring on the CV structure so that I can put electric fields exactly where I want them. So the concept of guarding is that concept of really controlling where my electric fields are so that they don't pass currents or capacitances that I don't want them to pass. Now, a nice side benefit of guarding this capacitance out of this cable is, remember the RC time constant we talked about? Remember, if this device is a teraohm and this cable has 10 picofarads of capacitance, we've got a teraohm and 10 picofarad RC time constant, which could be 50, 60 seconds or more to charge up. So if I guard this within 1%, say my voltage across my guard right here is 1% instead of the full voltage, I've reduced the capacitance by a factor of 100. I've reduced the settling time by a factor of 100. So guarding is really beneficial for getting good measurement speeds. So we just have a little example here of the difference between a guarded cable and an unguarded cable, measuring, in this case, 100 picofarads. The unguarded cable, not only does it have leakage current, as evidenced by the high current here, it takes a long time to settle. The guarded cable with reduced capacitance and reaches its final value much faster. Now, I personally have a test that I use that I call the step function test. I use that to give me a measure of the efficiency of the guarding in my system and how well my system works. Step function test is very easy. I use the custom list sweep capability. I build myself a 100-point sweep. The first 10 points are at 0 volts. Then I step to 10 volts. And the next 100 points are at 10 volts. And I measure the current. And what I expect to see is at 0 volts, I see the leakage current of the system. That's the internally generated currents. When I step to 10 volts, I immediately see a lot of current, and then it starts to come down. That's the RC time constant of the system. And when the system reaches low on the RC time constant, hopefully 100 points is enough, the delta between that and where I started is the leakage current of the system. So I get the offset current, the RC time constant, and the leakage current of the system. The step function test is a great test for testing the efficiency of your system and of characterizing your system. You're not always going to have the luxury of using a state-of-the-art system like the Keithley 4200. In some cases, you may have other instrumentation, maybe some older source measure units. That step function test will tell you the quality all the way through your probe system. So what are self-generated currents? Boy, you know, wouldn't it be nice if we could take these self-generated currents and use them to like power the lights and stuff, right? Unfortunately, we can't do it, although there was a couple of fellas out at some university out west a number of years ago that claimed they had tabletop fusion, and turned out it was really just errors in their measurement, you know. They didn't like self-generated currents. Self-generated currents are extraneous currents that will add or subtract from what it is you're trying to measure. They can be offset currents, such as internal currents in the instrument, or they can be external offsets, insulators, cables, triboelectric, piezoelectric, stored charge, contamination, humidity. You take a little contamination, a little bit of humidity, and you make yourself a battery out of it. And that thing will generate picoamps, nanoamps. You can't power a light from it, but you can sure mess up a semiconductor measurement. So a triboelectric effect is typically in the range of, 1 femtoamp to 10 nanoamps. All right. Mechanical stress, say you take a piece of Teflon and you squeeze it. You know, Teflon flows. And as that Teflon flows, it's going to generate current. Typically in the range of femtoamps to single picoamps. Ceramics, mechanical stress on ceramics, typically down in the 100 attoamp to 100 femtoamp range. Ceramics are pretty good. However, if you pound on a ceramic, it'll make a lot of current. If you've got a really nice, clean epoxy circuit board, it might be in the neighborhood of 100 femtoamps. But if your epoxy circuit board, which most circuit boards and most instruments are made out of, might be in the range of 100 picoamps. Circuit boards are easy to contaminate. Okay. Now, instrumentation has internal offsets. It's what we call the input offset current. That's a small current that flows in the ammeter itself. Okay. Now, we build active ammeters. Our ammeters are really the input of an op-amp. Okay. And we consider op-amps, particularly in Engineering 101, we consider op-amps to be an ideal input device, right? Infinite input impedance. But the reality is they're not. Okay. And so op-amps have currents that actually they continually flow into them or flow out of their input. So they're not infinite input impedance. Part of the magic of what Keithley brings to this is we build really good op-amps. We don't generally use off-the-shelf op-amps. We build our own. And we get really low offset currents, really high input impedances. So these currents are something that are an error source. They're not measurable. They don't flow through the measurement element. Okay? In some cases, your input offset currents can be brought down within spec by performing a system calibration. Now, as it turns out, the Model 4200 actually, by its nature, by its design, doesn't require a calibration to bring the offsets down, or periodic calibration. But some other instrumentation requires a calibration every half an hour or some other means of bringing the offsets down. Okay. So the offset current of the 4200 can be displayed by graphing the current versus time of an SMU with nothing connected. Okay? Now, when you're measuring current, you don't want to put a short circuit on it. You can cap it, but don't short it. And then just see how much current flows. The SMU will measure how much offset current is in the system. Okay? Now, this particular system here, the minimum range is 100 nanoamp full scale. So the sort of offset current you might expect to see out of this system is 1 or 2 picoamps. That's kind of what we're showing here. Well, actually, this is a femtoamp measurement. This is with the preamplifier. So this system here, there's always a picoamp or 2 flowing in and out of the terminals on this system. If you're trying to measure something under a picoamp, you're not going to get it with this system unless you upgrade it and add the optional preamplifiers. Okay. So in this particular case, we measured on the 100 picoamp range, we got about 6 femtoamps of offset. And then when we went down to the 1 picoamp range, we got about 2.5 femtoamps of offset. And you see the difference in noise also. But that brings up an interesting point, because the current range in a source measure unit defines its input and output characteristics. So the lowest current range on the 4200 with the preamplifier is a 1 picoamp full scale. It has about 10 to the 16th ohms of input impedance. The specified offset is guaranteed for a year, traceable to standards at under 10 femtoamps. Okay? And once you measure the offset, you can compensate for it. You simply subtract it from your measurement because it really doesn't drift. Okay? But as you change range, the nature of the instrument is such that its input impedance changes. So if you're 10 to the 16th ohms on a picoamp range, you're about 10 to the 15th, roughly, on a 10 picoamp range, about 10 to the 14th on the 100 picoamp range. So roughly the input impedance of the instrument goes up by an order of magnitude with each current range that you go up. So by the time you get to the 1 amp range, you know, you're running probably 1e to the 6th, sort of a mega ohm of input impedance on the instrument. So triboelectric effects are very interesting. This is friction motion at the boundary due to cable motion. I always like to say we're basically rubbing electrons off, okay? And, you know, if you got a cable, it has a radius. So as you bend that cable, which is just a small flex, the inner part of the cable bends at a different rate than the outer part of the cable. You get rubbing on that cable, it rubs electrons off, it generates current. That's a triboelectric effect. Okay, that triboelectric effects are one of the reasons Keithley developed an external preamplifier so that the preamplifier can be mounted right at the probe tips. So there is no cable to flex, or it's out so short it doesn't flex. And we can actually get down to sub 1 femtoamp measurements by having that preamplifier remotely mounted. Now, most people don't need that. And Keithley's special low noise cable has been developed to minimize these triboelectric effects. So with our low noise triax cables and coax cables, with our cables, you get minimum effects here. You don't begin, if you actually go in there and wiggle the cable, this is a fun experiment to do actually. Just go out there and wiggle the cable while you're running sampling. You can usually see on our cable in the neighborhood, certainly under 1 picoamp usually, from wiggling the cable. Right? So if you're measuring a picoamp or 100 femtoamps, it doesn't matter if you have the cable on there. It's really, you'll probably be okay. But if you're using somebody else's cable, they can generate, I've seen nanoamps of current generated just by wiggling the cable. Right? So to reduce triboelectric effects, you use low noise triax cables that we supply. These are special cables. We have them specially built for us. You keep the connections away from temperature changes because that causes things to expand and contract. You remove or mechanically decouple vibration sources. You know, one of the great examples I have of this was we had a really inexpensive probe station. When I first started at Keithley 23 years ago, we had this inexpensive standalone probe station. It was a chuck in a box, is what it was. And we didn't even have a vacuum pump. So they had went out and bought these little thing called a fish pump. This is the pump that blows air into your fish tank. And they hooked it up backwards so that it would suck vacuum so we could pull and then they set the fish pump down on the table. So it was the fish pump running on the table, right? And that sit there and that wiggled the whole system, and that wiggle was enough to generate, you know, 1s of picoamps of noise on our probe system. So it's best to tie down your cables. Now remember, this is if you're doing really sensitive measurements. If you're under, my rule of thumb is 10 picoamps. If I'm actually trying to get stuff under 10 picoamps, I need to take care of getting the cables tied down. So a lot of people will take the instrument and set it over there and loop the cables over here and hook it up to the probe station. So that cable is sitting there and maybe the air conditioning's blowing on a little bit, or people walk by. The one I really like is when your lab partner stands there and you're waiting for the measurement because it's a low current and he's kind of fiddling with the cable. Just because, you're standing there bored and you're going, yeah, you just blew my measurement, man. Okay, the piezoelectric and stored charge effects. So, this is an effect that comes about from a mechanical jolt, right? If you apply a force and you have an insulator that has a piezoelectric effect, that insulator is going to generate current. So, the key is try to use insulators that don't generate current. Well, while ceramic's very nice, it is very piezoelectric, okay? The example I like to use for the piezoelectric effect is a piezoelectric speaker. Tweeters oftentimes will be a piezoelectric speaker. In other words, if you apply voltage to this piezoelectric material, it's going to move, okay? Or if you move it mechanically, it's going to generate voltage. A piezoelectric microphone, right? So these effects, when we're measuring the currents at the level we're measuring, can be significant. In particular, sometimes we'll see it when people start to use ceramic standoffs or ceramic probe cards and they put them under stress. That's sometimes when we start to see piezoelectric effects. Now, offset currents by contamination and humidity, really this is an electrochemical effect. It's a battery. If you've got a couple of insulators here that have some contamination in there, and you add a little bit of moisture to it so that it has a little bit of a solution to it, it'll actually generate currents. And it's a huge problem for us in manufacturing at Keithley. So every printed circuit board we manufacture, we have to make sure it's very, very, very clean. And that cleaning process is a very expensive process. And it didn't get any cheaper when they made us get rid of lead solder. When we got rid of lead solder, we had to go to all new fluxes and cleaning processes. So the point is that contamination and humidity create a problem. You usually have direct control of the humidity, and you can keep it low. The other thing I see people frequently do, they just stand there and they'll fiddle with a cable, and they'll flip around the cable and they'll finger the end of the cable. You get your fingerprints on cable Teflon insulators and you've contaminated that insulator. And it's very hard to clean it up again. The same with probe needles and things like that. So you really don't want to touch anything that you're going to try and get low current measurements out of. Oop, no fingerprints. Just a little chart. By the way, this chart came out of the Low-Level Measurements Handbook. I think you all got one of those today. Just gives you some idea of the material impacts, which things absorb water, which things have piezo and triboelectric effects. These are some of the magnitudes of some of the currents that you can see. Triboelectric effects, standard cables can be up to tens of nanoamps. Contamination effects up to tens of nanoamps. Of course, Teflon is subject to mechanical stress up to picoamps, and of course, resistor noise is just Johnson noise. Briefly again about noise and source impedance, source resistance. The source resistance of a device will affect the noise performance of the SMU. As the source resistance of your device decreases, your current noise increases. So your minimum recommended source resistance is based on your measurement range. So the noise gain of a circuit is given over here. The output noise is the input noise times 1 over RF RS, where RS is your current source and RF is your feedback ammeter. Remember that SMUs are all feedback ammeters. So the source that you have here will impact the measurement you have here. That perfect example was the conversation we had at lunch about the nerve endings. What is the source impedance of a human nerve ending? I personally have no idea, but it's got to be relatively high. So if you're measuring low currents, the minimum recommended source resistance is pretty high. As your currents go up, your source resistance can go down. This is directly related to both the interaction of the instrument and also to Johnson noise limits. Johnson noise limits are one of those noise limits that I lost a slide on last night that we didn't get to talk about, that are generated, self-generated just by the temperature and the bandwidth of the material that we're using. Will self-generate noise. So why do we talk about this? Because the research that you're doing here at Purdue, you're working with many different types of new materials and things that you need to know what these properties are on those materials, and you need to know how it's going to impact the characterization and the measurements you make. You'd sure hate to scrap a new material you're working on because the thing is noisy and you think it's got a very high 1/F self-generated noise, when really it's just you don't have it connected properly. Noise and source impedance. When the SMU is an ammeter, don't short it and think you're going to measure the noise. So how do I turn an SMU into an ammeter? What I do is I tell it to source 0 voltage, and it's now an ideal ammeter. Actually, if I tell it to source a volt, it's still an ammeter. It's just an ammeter that is floating a volt off of common. But if you short an SMU, right, if you short the ammeter, basically what you've done is you put a short right on the input of this thing, and now you've got a noise gain of this internal feedback element versus basically 0. Basically, you're short. And so it makes no sense to short an SMU as an ammeter to try to measure its noise. That will not give you a result. If you want to measure the noise of an ammeter, you cap it as an electrostatic shield, but you leave it open circuit. So an ammeter is considered to be low impedance. Now that low impedance actually just means that it's at virtual ground. It's actually incredibly high impedance. It's isolated from ground. But the fact that it's an operational amplifier makes it at virtual ground. And you want to test it with an open circuit. So here's an example where the source capacitance of the device affects the noise that the source measuring unit can measure. As source capacitance increases, the noise gain also increases. So this is the summary of the low current and the high resistant measurement. Our 4200 reference manual, section 5, has very good details on low current, high resistance measurements, particularly as they relate to the 4200. The low level measurements handbook, 6th edition, has lots of good information on that. And there's also a number of application notes and white papers. Keithley.com, we are continually publishing application note, white papers, and online on-demand webinars.